Okay, welcome everybody. I'm Steve Hoberman. I manage Technics Publications, and whenever a new book comes out, it's wonderful to do a book celebration so that we could meet the author, learn more about why they wrote the book, some of the key messages in the book. So thank you for joining us. We're going to get started. I'm very proud to introduce Zach Bulgaris, who has written, this is actually his 7th book with our publishing company, Technics Publications, The Data Path Less Traveled. Zach has an amazing background. He is extremely strong technically, and yet he also has some great skills for explaining complex content. He has a PhD in machine learning. He is a proven data scientist. He's worked with a lot of startup companies. He has been a program manager at Microsoft. And he also has some great ways of explaining the content through his 7 books with us, through his many presentations at Data Modeling Zone, and even the way he presents his content. He has a very unique style of using mind maps, which is a great way to kind of get thought organized. So what we're going to do is it's a short presentation, about 30 minutes or so, and then there's time for Q&A. So feel free to listen and then have questions at the end. It's my pleasure to introduce Zach Bulgaris. Zach, welcome.
Thank you. Thank you very much, Steve. So that was a very flattering introduction. So at least less stuff for me to talk about when it comes to my first point about me. But just to elaborate a bit on the PhD stuff, when I was doing my PhD, that was the first time I got acquainted with the idea of heuristics and experimented with them. Because before I was in engineering and computer science, and then I went into machine learning and tried to improve things like everybody tries to do in a PhD. And in my PhD, I explored not just machine learning systems and algorithms, but also heuristics that can help improve the performance of the systems and come up with new systems based on these heuristics. So heuristics and I go back a long way. And since then, I've been very fascinated by them. It didn't stop after my PhD, and throughout my career in data science, whether it was working as a data scientist hands-on or as a program manager in Microsoft or as a consultant, as I am nowadays, I have been using heuristics extensively. And believe it or not, many data scientists also use heuristics, even if they don't realize it. But few people really understand heuristics in depth and use them more. So unless you're very, very knowledgeable about heuristics, this presentation is for you. Because I talk about heuristics, especially in this book, without assuming any prior knowledge. So in this short presentation, I'll try to do justice to this topic, which I can talk about for a long time. But I'll focus on specific things like what are heuristics, some data-oriented heuristics and their role in data work, optimization-oriented heuristics, how you can design and implement your own heuristics, and some supplementary topics about heuristics, and finally the bigger picture of heuristics and how they fit in the bigger idea. And of course, I'll provide some essential information about the book in case you're interested in reading and playing around with heuristics practically, like I did here. So let's start with some things about heuristics. First of all, heuristics are a very peculiar thing because it's not just one thing. You can't say that heuristics is just this and nothing else. Heuristics are basically a grouping of different metrics and methods. And these are all designed to solve specific problems and also facilitate data processes. So we don't make heuristics just because it's interesting programmatically, but also to add value to a business, to an organization. And all that comes through the solving of specific problems and optimizing processes and stuff. But why should you, as a data practitioner, care about all this? Well, first of all, heuristics are very useful in the stuff they do and very good at that stuff. They may not be applicable everywhere, but in the niches that they are applicable, they add a lot of value. Also, not many people are very comfortable about heuristics and developing new heuristics. So if you learn about that, you definitely stand out from the crowd. And additionally, because they're pretty simple and easy to implement and integrate in different processes, you can do that and improve existing pipelines. You don't have to build new pipelines because of a new heuristic. You can just stick it there, whether it is to improve EDA work or to improve some ETL or some analysis work, and improve the whole process, the whole pipeline. And finally, they're very creative and very fun. So it's not just work, but it's also play when it comes to heuristics. And this kind of playful approach is something I have tried to follow, both in my investigation of heuristics on my own, but also through this book. Heuristics are particularly useful in problem solving, as I mentioned earlier, and this thing that they provide, which not many other tools provide, is the creative aspect, the creative approach to problem solving. Because many people can solve a problem, okay? There are mathematical processes that are known for solving optimization problems, for example, but some of these are not really suitable for the difficult problems that we face today. Today, we have complex problems involving lots and lots of data or lots and lots of variables. And what do you do with those problems? You can't tackle them with conventional methods always. So that's where heuristics come in and save the day in a way, because they allow us to simplify the problems and solve them in a more creative way. We may not get a perfect solution, but oftentimes this is not even required. We just need to find something that is good enough. And in the business world, you see that very often. Like, you don't wait until you have the perfect product or the perfect service before you release it to the public. You gradually improve it. And the same thing is happening with heuristics as well. You often see heuristics evolving over the years. And of course, depending on how you see heuristics, there are different categories of heuristics. As I mentioned before, it's not just one big group, but also different kinds of heuristics here and there for different problems. So if you want something to measure something, you can have a metric. If you want something that requires some processing of the data, some more heavy lifting work to derive some useful conclusion about it, or some analytics, some basic analytics that cannot be done with a data model, then you use some method. So there are metrics and methods as heuristics depending on the implementation and the work required under the hood. Now, depending on the design complexity of a heuristic, you can have the basic heuristics that most people use, or you can have the meta heuristics, which are more advanced, more sophisticated heuristics that often employ other heuristics on the back end or other processes. And there are usually standalone algorithms that do a specific task, and they do it really well. So there are these kinds of taxonomies to help us understand them better, and also to help researchers investigate all that stuff more. Now, there are many use cases about heuristics in data work. Most of them involve EDA work, also learning more in-depth stuff about the data, evaluating models, developing new models, and also innovation and research. And there are some various commonly used heuristics. I have here a small list that you can look at. Accuracy rate and F-score. These are stuff we often use in classification work. Mean square error and absolute error in regression more problems. Most distant metrics are actually heuristics, and there's a plethora of those that is always growing depending on the distance they want to calculate, depending on the space that we're working with, because some large dimensional spaces require different approaches than the conventional basic metrics that we learn in the university. K-means clustering and other variations of it are also heuristics. And most modern optimization algorithms, like the PSO and genetic algorithms and simulated annealing, for example, are all meta-heuristics in a way. Entropy, the entropy metric, is a heuristic, and of course, kernel PCA. Although PCA itself is a statistical method, the kernel PCA variation of PCA is a heuristic, or a meta-heuristic rather. And beyond that, there are many, many more. The key characteristics of a heuristic are that it's data-driven. It's often work in progress. That's always improving. And although it's imperfect, a heuristic adds a lot of value for something. It helps us facilitate something really well. And finally, it involves a bit of creativity, sometimes a lot of creativity, especially during its development. So let's now look at some data-oriented heuristics and how they add value. first of all, we have some basic heuristics for EDA, which I described in the book. I can't tackle all of them, so I just focus on two categories. One for binary variables, so binary similarity heuristics, like the Jacquard similarity, which is very commonly used in real life, and also continuous variables and heuristics based on those. Here I have an example of the range-based correlation, or RBC, as I call it, which is a heuristic I developed using a basic geometry, nothing really fancy, to find the different correlations that are also non-linear. So not just a linear correlation that the correlation coefficient gives us, but something beyond that. Advanced heuristics for EDA work are, for example, density, which I cover a bit in the book, and also the index of discernibility, which I also cover, and which is also something I've developed during my PhD. These are sophisticated heuristics, but still, if you understand the ideas, they're not that complicated. And once you start applying them, you see the breadth and depth of the value they can add, especially when it comes to whole data sets, because the basic heuristics usually work on the variable level or specific data points, but the advanced heuristics usually work on a larger scope, and they can handle whole data sets at once. Model-related heuristics include the Jacquard similarity that I mentioned before, because oftentimes when we want to correlate the outputs of a classifier with the target values, we need to do that somehow, and the Jacquard similarity manages to do that really well, as well as the F scores, especially the F1 score, which is used primarily. There are other things like the mean square error, and even the RBC metric, which I mentioned for EDA, can be used for model-related analysis for regression problems particularly. And there are other ones beyond that, but these are the ones that I focus on in the book. Additional heuristics that I also cover are the index of peculiarity, which actually I use as a case study for developing a heuristic from scratch. And I developed those days that I was writing the book. Also the entropy heuristic, which is very well known from information theory, and the ectropy heuristic, which is like the inverse entropy in a way, but not exactly. And it takes values between 0 and 1, so it makes it more easy to interpret and understand, and which has a very interesting role to play in cybersecurity applications. Now, beyond the data-oriented heuristics, we also have the optimization-oriented heuristics, which are also the most well-known. If you look in the literature, or if you see other books about heuristics, they usually focus on those because these are the most mature ones. And the reason why they're most mature is related to the rationale of optimization-oriented heuristics. Why you bother with those? Like, we have already a lot of optimizers in the literature, which are very sound mathematical processes that give you the perfect solution. So why bother with heuristics in that sense? Well, in most problems that involve lots of data, or especially lots of variables, you can't really work with those conventional optimizers. They just take forever to converge. So you have to find another approach. And most of the time, we don't really care about the perfect solution anyway. So if you find something that's good enough, like say, for example, you're trying to find the solution to the traveling salesman problem, you don't care if it's the perfect path, as long as it saves you time and you go through all the different cities as a salesperson and stop through all of them without spending too much time traveling back and forth, then that's good enough. You can save you lots of money when it comes to gas and lots of time, actual time. So we don't care about the absolute best solution, and heuristics don't provide the absolute best solution anyway, so it's perfect when it comes to optimization. The main methods for optimization that I cover in this book are PSO, which stands for particle swarm optimization, and the GAs, the genetic algorithms. But I also mention other metaheuristic optimizers as an example. And all of them are very important because they approach the whole problem of optimizing stuff in a very different way. Like PSO, for example, approaches the whole thing as a collection of solutions that form a swarm, just like a swarm of insects, for example. And they all move together somehow towards the perfect solution. They may never find the perfect solution, but they go very, very, very close to it. And that happens very quickly as well. So something that may take hours or even days for a conventional optimizer to attain, for the PSO, it may take minutes. So it's a very powerful methodology. And of course, it involves a lot of randomness. So every time you run, it has a different result, but it's always very close. And it's a very interesting approach because all the different solutions work together. So it's like a teamwork approach instead of just having one solution that evolves. The PSO method has been around for about 30 years. In 1995, it made its debut. And there are lots of variants to it. I've actually contributed to the PSO development by developing a couple of variants of my own during my research days. As far as genetic algorithms are concerned, they have a different philosophy altogether. They're inspired by the field of genetics. So everything has this genetics terminology when it comes to GAs. And for example, the solution is coded as a gene, and you have different genes, and all of them put together they form this population, which is the genome. And over the different iterations of the algorithm, the different generations, as they're called, they evolve. And how they evolve, you select randomly some of them. And of course, this is not entirely random. It has to do with how good they are. So you don't just get the garbage solutions that much as you get the good ones. And then you do a crossover thing where you mix and match them somehow. And finally, there's the option of doing a mutation on one or more of these solutions, also randomly, to make more diversity come about. So this simple paradigm of these three different operators, the selection, crossover, and mutation, is enough to create a very powerful new solution, which is not in the original random ones, but it's some kind of combination of them and also random mutation. And that's very, very powerful for discrete problems, particularly. The traveling salesperson problem that I mentioned before is really well tackled with GAs, as well as other logistics problems. And even in modern problems involving large neural networks, GAs play an important role because that's one option of making the optimization happen for the weights involved. Beyond these two families of optimizers, which are very powerful meta-heuristics, there is also other meta-heuristic optimizers, such as simulated annealing. This involves a process that emulates the cooling of metals. And it's a very interesting approach because unlike the other ones, this uses a single solution and it tries to improve it over time. It's not so intuitive as the other ones. It has a bunch of parameters that are very difficult to get the hang of, at least initially. But once you get it to work, it works really well and always gives you a good solution. Not the best solution, but something pretty good. It doesn't get trapped in local optima, as they call them, like solutions that are good, but not that great. And no matter how you evolve them, they don't get very far. So this guarantees a pretty good solution that is close to the global optimum. And although I don't cover it in this book, I cover it in another book I have co-authored with Yunus Bulut, the AI for data science, which you can find here. And it's a very interesting way to get into optimization if you're new to all this. Beyond all these optimization meta-heuristics, there is also the optimization ensembles, which is a different animal altogether. Just like we have ensemble classifiers, for example, or ensemble regressions, you also have ensembles of optimizers, which combine the strengths of different optimizers in a single optimization system. And this can be done in different ways. So there's a lot of creativity involved there as well. And of course, wherever there is this kind of structure and process involved, there is often heuristics involved too. So you may have heuristics for developing the final solution of the ensemble, for combining the different optimizers in a good way. Or you may find heuristics are very useful in figuring out when to stop using one optimizer and start with another one, because there is also ensembles that involve different stages of optimization. You start with a different optimizer, with a certain optimizer, and then once it finishes, another one picks up from where the other one left off. So you get really the best of both worlds this way. Because some meta-heuristics are really good for finding a generally good solution. Other ones are very good finding a really good solution starting from an already good solution. So you get this kind of trade-off often. And of course, there's always randomness involved, but this is part of the whole process. That's quite common in all these modern optimizers, by the way. Even the variation of gradient descent, which is often used today, the stochastic gradient descent, involves a lot of randomness too. So now to the fun part of this whole topic, which is the designing and implementing new heuristics. Now, there's no set formula, but I provide an interesting framework that you can use for getting from the ideation stage of a new heuristic to the implementation. Because at the end of the day, it's not really that difficult. It just takes a lot of planning and a lot of refinement. So you start originally with objectives and the functionality of the heuristic. The objectives are basically what problem the heuristic tries to solve and what you expect out of it. Like, are you looking for a particular metric or a measurement of something, or do you want some new vector of values that represent something? That this is something that you have to identify when it comes to the objective definition. The functionality is the how of all the heuristic. So what does it do exactly? Like, if you were to code this, how would you code it? Like, can you draw it up in a diagram? Of course, this is easier said than done, but it's a good first step to understand that, this is how it's going to do it. Sometimes, if it's a very complex task, you may need to break it down and have different parts that are done by different heuristics. So that helps you plan out the whole thing. And then you have to define specifics like the parameters of the heuristic, which is basically all the moving parts. And often they are related to the inputs of the heuristics when it comes to implementing it as a function in programming. The outputs are similar to that. It has to do with what this function yields as outputs, and these are directly related to the objectives. And finally, there's the usability of the heuristic. You have to really think about this quite a bit and work on it too, because just because you have a good idea and that can be implemented really well doesn't make it usable. Like, the usability makes it real, like in the real world, how applicable it is, what are its limitations, how is it, how does it work? Can you provide some documentation for it so that somebody can pick it up and use it? And also things like what kind of variables are involved? Is it user-friendly? Things like that. All these come under the usability umbrella. Related to usability is the scope of the heuristic, which is often considered as part of the usability. And I often describe them together, usability and scope, because the scope is all about the applicability of the heuristic, what kind of problems, what variety of problems it can solve, how scalable it is, and things like that. So it's good to define all these things beforehand, and then you can start implementing it through the development stage of the heuristic, where you go from the paper to the code and you try out different things. And oftentimes you have to go back and refine things because they don't always work as you imagine. And eventually you come up with something that works and gives you the results that you expect. The thing is that, this can always be improved. And that's why the optimization part of the heuristic is also an important thing to consider, because you can always make it a bit more efficient. Maybe you can use some other approach for figuring out distances and stuff. For example, I discovered that the k-dimensional trees are a very powerful way for multidimensional data sets and figuring out distances there. And this can improve a heuristic greatly, especially if it involves this kind of calculations. Beyond that, you can make it more scalable and more parallelizable, because some heuristics involve lots of computations that can be parallelized. So if you use different threads in your computer, you can assign different tasks to different threads, and this way come up with a result much, much faster. Now, some supplementary topics about heuristics are also important. I won't go into too much depth here, just focus a bit on the limitations of heuristics, because we tend to forget when we're engrossed in using a particular heuristic, we tend to forget that it doesn't really solve the problem, all the problems in the world, or it doesn't tackle all the different variables that you can find. Some of them are limited to just continuous variables. And if you try to work with them using ordinal inputs, they may not really work so well. Other ones work really well with categorical variables. So you have to really understand that they have their limitations. And some of these limitations nobody may know about, like not even the creator of the heuristic, because they're not really discovered yet. The fact that the heuristics are just so data-driven makes them very widely applicable in a way when it comes to different kinds of data, different distributions of data, for example. So you may find that for a particular kind of data, the heuristics don't really work very well. And that's something that you discover through the testing phase of heuristics over time. It's really hard to foresee that in advance, but if the heuristic is documented properly, you can avoid some of the limitations that are already known. Now, beyond the limitations, of course, there's a lot of potential for heuristics, not just in the specific thing that they were designed for, but also other areas. For example, I didn't realize at first that this range-based correlation heuristic, although it was good for ADA, it was also very good for figuring out if a particular regression system is good. It's not perfect, but it works there too. So there are lots of potential, there are lots of possibilities with the heuristics that I have described here in this mind map that is included in the book. I'm not going to go into this into detail because it's so much to say and I don't have that much time. Suffice to say that the data summarization part is something I'm very experienced with when it comes to heuristics used for this kind of task, because to the best of my knowledge, this is not easily done otherwise. Unless you have a very advanced AI system, it's really, really hard to do data summarization properly. You can do sampling, which is a different process, but summarization, and not talking about just a single value, like you can summarize a variable with a single value, but that's not the same. I'm talking about summarization of a whole data set, having multiple dimensions and summarizing it with a smaller number of data points. That's something very tough, and heuristics provide an option for that, at least in potential when it comes to really large data sets. But for ones that are about 1 million data points large, you can easily do that with heuristics in a single computer. Beyond that, you may need to do some parallelization techniques. But the bottom line is that all these are potential areas of improvement in data work through heuristics. I would be bad to not include the transparency aspect in this talk about heuristics, because it's really something that is a hot topic nowadays, especially when it comes to AI. We talk about black box models, and that's unfortunately the state of the art nowadays for most advanced predictive models. We don't really know how they work. There's very little explainability, if at all. But through heuristics, you can definitely improve on that. And I know for a fact that the distance-based heuristics can easily be explained through distance-based models can easily be explained and become more transparent through specific heuristics. Of course, not all heuristics can help with transparency, but some of them can. And others can help you in other ways, like efficiency, for example. Now, regarding the bigger picture of heuristics, if this whole heuristics journey is like a path through this mountain, the bigger picture is basically what you view when you reach the summit. That's why I have a different picture here. And the bigger picture involves the bigger paradigm that heuristics are part of, the data-driven paradigm. And that is particularly popular nowadays, ever since AI has become mainstream. In a nutshell, data-driven paradigm has to do with using data as is, without wondering too much about what distributions are involved and what correlations are among the variables and stuff like that. We just use the data as is and do the best we can with it. So it is a bit like data engineering, but in analytics. So if we were to do all that and embrace heuristics and use them in our problems, we do two things. First of all, we solve the problems, but also we do something that is even more important, in my opinion, which is to express and improve our creativity. And this creativity is a very powerful thing to have in problem solving. How do we do that? Well, heuristics allow us to view data differently and tackle problems in a different way. So through the use of heuristics alone and the selection of the different heuristics and getting to know how they work, it helps us think in different ways. If you want to go a step farther than that, then you can develop your own heuristics. And just the function of developing something new from scratch, something that works as well, is an act of creativity, both for expressing it and improving it. And that translates really well in how you view problems in general, because you can have a different outlook to them and come up with solutions more easily. Beyond that, heuristics are also a powerful educational tool. If you are new to a field and you are introduced to heuristics early on, you get to view the possibilities that they express, because the heuristics are not just this or the other tool only. They are they're a way of thinking, in a way of thinking practically about problems, because in real life, we don't really care about the perfect solution, and heuristics don't care about perfect solutions either. They just care about finding a solution quickly, a good solution in a fast manner. So they educate us in a way to think this way, to think practically, to think like a good engineer, for example. And beyond that, they also help us view data differently because they approach data in different ways. They measure different things in data that other metrics that we know may not be able to do. So they can also help us think of information and data in different ways, and how information can linger in data in places we don't normally look. So if we were to do all that and educate ourselves through heuristics and express our creativity and improve the creativity as well, and become acquainted with heuristics and where they come from and how they come about, then we can even think about a new era of analytics that is more based on heuristics. Like heuristics can be like the go-to way for solving problems, instead of just using some model-based approach, which is also very valuable, but for difficult and modern, like the modern problems we face, sometimes the heuristical approach would be better. And thinking in this way can help us improve analytics overall, because we have learned that data by itself doesn't have any value, but the value comes from analyzing the data, deriving insights from it. And heuristics, because they look at data in a deeper way, they can help us derive these insights more easily and even unearth insights that we wouldn't be able to unearth otherwise. So altogether, they can bring a better field of analytics in the future, not just for advanced practitioners, but also for other tiers of practitioners in this field. So if you want to learn more about all this, I really recommend this book, The Data Path Less Traveled, which is available at the Techniques Publications website here, but also on Amazon. And the book is not just text. I mean, it has a lot of text and diagrams and nice schematics to explain the concepts and the thinking behind everything, but it also has a lot of code. The language I use is the Julia language, because it's very easy to understand even if you don't know it. And it's also very easy to code in it if you're a newcomer to this. And also it has its own kind of code notebook. It works on Jupyter, but here I use the Neptune notebook, which is innate to the Julia language. And it's also very useful by itself, because a code notebook file can be accessed on a text editor. You don't need to have a specialized program. So if you don't want to use a code book, you can just get the code from the Neptune notebook file. If you're interested in this stuff in a more hands-on way, I'm also considering having a workshop. So you can let me or Steve know about this, and we can explore the possibility in the next few months. And if you're looking at getting the book with a 20% discount, you can use this code here when you buy it from the Techniques publication site.